Here we have a paper, the piece of paper with the width d, and that paper lays on a stationary table, but the paper itself is moving to the right with the velocity that has magnitude v, and that is the velocity with respect to the table. At some time, a coin moves from the table to the paper, and it has a velocity at 90 degrees to the edge of the paper, and the magnitude of this velocity is 4/3 v. Now again, this velocity is given with respect to the table. While the coin is on the paper, it experiences friction, and eventually it comes out from the paper at some angle with the edge of the paper. We don't know what this angle is, we just know that this angle is not zero. And the absolute value of that velocity is v. And again, this velocity is given with respect to the table. And we have two questions here. First question is, what is the velocity of the coin when it comes to the paper with respect to the paper? And the second question is, what is coefficient of kinetic friction between the coin and the paper? We know the velocity of this coin with respect to the table. So there's a simple formula that relates the velocity of the coin with respect to the table, velocity of the coin with respect to the paper, and velocity of the paper itself. So the relationship tells us that velocity of the coin with respect to the table equals the velocity of the coin with respect to paper plus velocity of the paper. So velocity in one coordinate system equals the velocity of another coordinate system plus the velocity of that second coordinate system with respect to the first coordinate system. So in our case, we know v in, the velocity with respect to the table. We know velocity of the paper, and we need to find this v prime. So we're just going to rearrange this equation. And now let's see what we're going to get. First of all, let's see what's happening when the coin gets on the paper. So let's say this is round thing is our coin. This blue line is the top edge of the paper. Now, we get v in, velocity of the coin with respect to the table. We get velocity of the paper. And now we need to subtract one from another to get velocity of the coin with respect to the paper. And by rules of subtraction of the vectors, this is the vector we're interested in. Now, to figure out what this velocity is, we need to figure out two things. First is the magnitude of this velocity, and second is the angle of that velocity with respect to the top edge of the paper. First of all, let's think about the magnitude of this vector. What we have here, as you can see, is a right triangle. We know two legs of this triangle, the red and green, and we are asked to find the purple hypotenuse. We have Pythagorean theorem to do this. And now if you plug v in and vp in this formula and simplify and take a square root, we're going to get our answer. So magnitude of the velocity of the coin with respect to the paper is 5/3 v. Now what about the angle, this angle theta over here? We also can find this. Well, we may not be able to find exact value for the angle itself, but we can find exact value for trigonometric functions like cosine of theta and sine of theta. So cosine of theta, cosine of this angle, is the ratio of adjacent leg, the green one, to the hypotenuse, the purple one, and we get 3/5 here. And the sine is the ratio of the opposite leg, the red one, to hypotenuse, purple one, and here we get 4/5. So we're done with this part of the problem. The next question is to find coefficient of kinetic friction. But before we do this, we need to write down all the forces that act on the coin. But before that, we need to choose coordinate system in which we're going to do this. And in this problem, the easiest thing to do is to deal with coordinate system with respect to the paper. The coordinate system in which the paper is stationary and the coin is moving. So that coordinate system is actually inertial coordinate system. And so in that coordinate system, the first and second Newton's laws are valid. The reason for that is if we assume that table is stationary and table itself is an inertial coordinate system, paper coordinate system is moving with a constant velocity with respect to the table, and therefore it's also an inertial coordinate system, and first and second Newton's law are valid in that system. So let's find all the forces that act on a coin. First of all, vertically, we can look at this coin. This is our coin, gray one, and the black one is the paper. So coin has two forces acting on it. Normal force from the paper going up, and the gravity force going down. The coin is not moving vertically at all. Vertical acceleration is 0, and therefore in absolute values, normal force should be equal to gravity force. So now if you say n is the magnitude of the n vector, and mg is magnitude of mg vector, this relationship is true. What about horizontal motion? We have a coin here, and this coin is moving with some velocity v prime. We put prime here because we're considering velocity with respect to the paper. And what we know here, there's only one force in horizontal direction, and that's a friction force. And the friction force is acting in the direction opposite of the velocity. So what we find here is the velocity and the friction force are on the same line. And what it means that although this friction force will be reducing the magnitude of this velocity, this friction force cannot change the direction of this velocity. And this force cannot turn the coin either left or right. The coin will continue propagating along the same direction, along the same line. So now if you look at this picture, and let's just use this picture and assume that what we're going to draw is in the frame of reference with respect to the paper, we find that coin is going to move along this green line, and the angle between the green line and the top edge of the paper will be theta, the same theta that we calculated right here. So now, what about the friction force? As far as the magnitude of this friction force, since the object is moving on the paper, we are dealing with kinetic friction force. And kinetic friction force is proportional to the magnitude of the normal force. So friction force in magnitude is mu times n, where mu is coefficient of friction, which we need to find. And since n is mg, so we get mu mg. On the other hand, we can use Newton's second law here in this coordinate system, and we know that friction force should be equal to mass times acceleration. We substitute mu mg instead of friction force, we get this equation. And from here, we find the expression for acceleration. This is a magnitude of our acceleration, and the direction of this acceleration will be the same as the direction of the friction force. So now the question is, how do we find this mu? We don't know it, and that's what we need to find. And to do this, we need to actually use the condition that is given in our problem about the velocity of the coin when it gets out from the paper. We said that magnitude of this velocity is v with respect to the table. But before we get to the velocity with respect to the table, let's first figure out what is the velocity of the coin with respect to the paper. So let's call it v prime out. To calculate this v prime out, we first notice that we are having an object to move along a straight line with a constant acceleration. And we know several formulas that tell us how to do this. The formula we're interested in now is this. It relates the velocity at the end, velocity at the beginning, acceleration, and the distance between the points of in and out. And that distance L is actually the length of the green line right here. Now there's one issue with this formula, the way it's written right now. Notice when the coin moves on the paper, it slows down because of the friction. Because of that, V prime out is going to be less than V prime in, and what you have on the left is going to be negative. On the right-hand side, all the terms are positive. They're positive because we've chosen to use A as a magnitude of acceleration. In this formula, acceleration could be both positive and negative. So in our case, acceleration we need to take is a negative number, and that's because the acceleration is in the direction opposite of the velocity. So to fix this problem with this equation, we're simply going to put a minus here. In this case, we can still keep A as positive. Now to calculate V prime out, we need V prime in. We already know that. We need A, we know that, and we need to know L, and that we don't have yet. But we can easily find L. Notice that we have a right triangle here. L is a hypotenuse of this right triangle. But we also have D, which is known to us, and this is a leg. And we know angle theta right here. So using that information, we can easily calculate that L should be D over sine theta. And we know what sine theta is. Now we're going to plug all these values into this equation and get the equation for V prime out. But the next thing we need to do, we need to convert this V prime out, the velocity with respect to the paper, into the velocity with respect to the table. Now we're going to use the same formula as before. Velocity with respect to the table is velocity with respect to the paper plus velocity of the paper. Now let's see how it's going to work and how we can find V out. Again, let's consider a coin and a boundary of the paper. In this case, it's a bottom boundary. We have V prime out, this guy, velocity with respect to the paper. We also have velocity of the paper. And now we need to add these two vectors to get velocity with respect to the table. Now notice this angle between the horizontal line and V prime out is theta. Also notice that blue line and green line are parallel. Therefore, this angle between purple line and the green line is also going to be theta. Those two angles are what's called alternate interior angles for the parallel lines, and they have to be congruent. And now we got ourselves a problem where we know two sides, angle between them, and we would like to know the third side of the triangle. To solve this problem, we need to use what's called law of cosines. Now let's remind ourselves what law of cosines says. It says that if I know side A, side B, angle between them, I can use this formula to calculate side C. Now we're going to apply this formula to our triangle, and if we do, we get this formula. Now it looks scarier than it is. We can actually simplify this significantly. First, notice that V out is the magnitude of the velocity of the coin when it's coming out of the paper with respect to the table, and that's going to be V. Vp is also V. So we have V squared on the left, V squared on the right. We can cancel them out. The next thing we're going to do, we're going to just move this term on the other side of the equation. Next thing, notice that there is V prime out on the left and on the right. And V prime out is not 0, so we can cancel it out. And when we do, we get this equation, which is very, very simple. We know everything on the right. On the left, we would like to use this equation. But this equation actually for not V prime out, but V prime out squared. So to fix that problem, we're just going to square this equation. And now we're going to substitute V prime out squared from here to the left-hand side. Now Vp, we know it's V, and cosine theta, we also know it's 3/5. If you substitute, we get equation like this. Notice that we know everything in this equation except for the mu. It is a linear equation for mu, which we can easily solve, and if we do, we get the final answer.